I left off in the last video having generated a map of last names and counts using a parallel stream. Although this code seemed to work fine, it's not how you'd want to write this code. I've got that project open, which I called the Parallel Streams and More project. I'll start out by printing the type of the map that got returned from that last stream pipeline. I'll print the class name of the map instance, last name counts. I'll run this code. The last thing that's printed out is from this new statement, and I can see that the type I get back is the java.util.hashmap. You might be surprised to learn that the hashmap, as well as the other common collection implementations like ArrayList, LinkedList, HashSet, and TreeSet, aren't thread safe. The hashmap, like the other mentioned collections, lacks synchronization. This class doesn't provide any internal synchronization mechanisms to ensure thread safety by concurrent processes. As a result, two or more threads modifying the same hashmap can interfere with each other, leading to issues like lost updates, infinite loops, or inconsistent data. There are also no guarantees of memory consistency while iterating. When one thread is iterating over a hashmap while another thread modifies it, there's no guarantee that the iterator will reflect the most up-to-date state of the map. This can lead to concurrent modification exception or unpredictable behavior during the iteration process. Let's pull up Java's API documentation for the hashmap class for a minute. I'll scroll down just a bit until I see a note in bold. The note says that this implementation, meaning the hashmap, is not synchronized. If multiple threads access a hashmap concurrently and one of the threads modifies the map structurally, it must be synchronized externally. A structural modification is any operation that adds or deletes one or more mappings. Merely changing the keyed value doesn't count as a structural modification. We also learn here that we can wrap the hashmap with the collections.synchronizedMap method. This method can be easily used rather than writing your own custom code each time you want to synchronize this class externally. I'll be talking about this method in just a minute. But first, let's talk about iterators while we're still looking at this documentation. These are all fail fast, as it explains here, and throw a concurrent modification exception when concurrent modifications are made. But what I'll point out here is the statement that says it would be wrong to write a program that depended on this exception for its correctness. Okay, so what does all this mean? Although the hashmap isn't thread safe, each parallel thread will actually have its own copy of a map instance and won't be contending with another thread for access to a single copy. When the thread's complete, however, the code operates by merging two maps together by key. This type of merge is computationally expensive, so it's recommended that for maps, you don't code your parallel streams this way. I'll change my code here to use a different collectors method, which is more efficient for parallel streams. This is as simple as changing grouping by to grouping by concurrent. If I run this code, I still get 10,000 counts total, distributed somewhat evenly over the 6 last names. What I want you to notice is the class name of this new map instance that comes back from this stream pipeline. Instead of a hashmap, I've now got a concurrent hashmap. This is a class defined in the java.util.concurrent package. The concurrent hashmap is one of several concurrent classes in this package, and I'll be talking about these more shortly. First though, I'll do something I don't want you to do in real life, if you can avoid it. I'm going to create a pipeline stream that has side effects, meaning it's going to change the state of an instance that's not part of the pipeline. To do this, I'll set up a treemap variable manually before I execute the stream pipeline. I'll create a scenario where the map already exists. In other words, the stream won't create the map, but it will add or change data in the map. I'll generate a stream of 10,000 persons as I did before. I'll make this a parallel stream. In the forEach method, I'll use the map merge method to merge data into the existing map. If the last name isn't in the map, this should add the last name with an initial value of 1 to start. Remember, this kind of change, where I'm adding a key, is a structural change to the map. If the key exists, this code will just add 1 to the existing value. Finally, I'll print out this map. I'll copy my code that prints the total counts using the map values. I'll paste it after this last pipeline. I'll change the name of the variable in this pasted code from last name counts to just last counts, which is the name of my tree map variable. I'll run this code. The output of this code is going to be unpredictable. Under many circumstances, I'll get an exception when the merge method is executed in the stream. I get a concurrent modification exception from the stream pipeline code while it's trying to use some kind of iterator. I'll run this a couple of times until it actually hopefully completes without an exception. You can see the last names are in order, but notice the total counts in the map. I get less than 10,000, which is how many elements were in the stream. This code, the way I have it coded, using a tree map with a parallel stream making updates to it, potentially has many different kinds of problems. The first was the concurrent modification problem, and the second is probably due to memory consistency errors. These are just some of the problems that can occur when you use a class that's not thread safe in a multi-threaded operation. Using it with a parallel stream, like I'm doing here, really demonstrates the problems. Now, I'll change my tree map variable to a different type of concurrent map, changing it to a sorted concurrent map called concurrent skip list map. I'll run this. You can see that this map is still sorted by last name, but it didn't get any exception, and I'm also getting 10,000 counts in my map here. I'll run it a couple of times and confirm it works each time. Using a concurrent skip list map is one thread safe option. To show you another, I'll revert that last change. This time, I'll wrap the instantiation of the tree map in a call to a synchronized wrapper collection. I can do this by calling a method on the collectors class called synchronizedMap. I'll run this code. Notice that the last names are again sorted, that this map also has 10,000 records. The type was printed in this output too, and this is a special type on the collections class called synchronizedMap. I'll run the code a couple of times. And here too, you can see I always get 10,000 records back, and I'm not getting any exceptions. So you can see you have several options to choose from. I've run through these pretty quickly, so now let me show you some of these special map types on a slide. You're already familiar with hashmap and tree map, and hopefully you remember that a tree map is sorted. Neither of these classes is thread safe, and both should be avoided when you're working with parallel processes if multiple threads are accessing them asynchronously. I've included the type of collector you might use if you were collecting stream pipeline data in either of these cases. By default, the grouping by collector returns a hash map. To get a different type of map back, you would specify your own map type using the collect method, which is show for the tree map. There are two concurrent classes in the java.util.concurrent package for the map. These are concurrent hash map and concurrent skip list map, and this last one is sorted. There's also a synchronized class we can get by using a static method on the collections classes. Only the synchronized map is considered a blocking type of the three thread-safe types shown on this slide. This means other threads will block, waiting for access to the map. That's one of the big differences between synchronized classes and concurrent classes. Both concurrent and synchronized collections are thread-safe and can be used in parallel streams or in a multi-threaded application. Synchronized collections are implemented using locks which protect the collection from concurrent access. This means a single lock is used to synchronize access to the entire map. Concurrent collections are more efficient than synchronized collections because they use techniques like fine-grained locking or non-blocking algorithms to enable safe concurrent access without the need for heavy-handed locking, meaning synchronized or single-access locks. Concurrent collections are recommended over synchronized collections in most scenarios. Okay, so I've started with the map because it's often used with parallel streams to collect and aggregate data from large datasets. Next, I'll show you examples using other collection types. For arrays and lists, you can use the terminal operations to array or to list respectively with parallel streams. Again, This means each parallel process will be collecting elements first in its own array or list, and the final part of the stream process combines each thread's data into a single source. Let's quick look at these. To demonstrate these, I'll start with a new class and call it mainLists in the dev LPA package. I'll add a main method in this class as well using PSVM. I'll start with a variable called persons, and I'll just use local variable type inference, so var_s the type. I'll generate a stream of persons, again limiting it to 10,000, and running it as a parallel stream. I'll call the toArray terminal operation, and I'll pass the method reference. That's a constructor for a new person array. And just a reminder, if I didn't do this and just had no arguments, I get an object array back rather than a typed person array. I'll print the total number of array elements out. Running this code, I'll see that I get 10,000 records in my array, and the inferred type is an array of persons, so this is good. There are some instances where you may include the parallel operation, but the stream's pipeline manager may not actually execute it in parallel. Let's see if this is the case in this instance. To do this, I'll set up a concurrent map variable that'll collect the thread names and count the total processes each thread executes. This map will be keyed by thread name and contain long values. I'll use concurrent skip list map in this case, which means it will be sorted by the natural order of the keys, so alphabetically by thread name in this case. Next, I'll use the peak intermediate operation, inserting that after parallel, but before the toArray terminal operation. Each element in the stream is a person record, so I'll use P as my lambda expression argument. I'll get the current thread name. I'll strip out part of the name if it contains information about the common pool worker and replace it with a shorter thread name. I'll merge the thread name into the map with what is the initial value, or summing the values for each processed thread. Okay, so let me just say, I don't recommend that you use the peak method like this in real life. The peak method is usually used for some sort of debugging code, and here, my debugging code is creating side effects. In this case, it's intentional because I'm using the code this way just to demonstrate how to examine which threads are doing the work. Next, I'll print this data out. First, I'll just print out the entire map. Next, I want to add up the values in each entry, so I'll set up a total variable, along. I'll loop through the thread map's values. I'll add them to total, and I'll print the total, calling it thread counts. If I run the code now, I'll see how the work was distributed across different threads, and I can confirm this is really running in parallel, and then it accurately collected 10,000 values on my stream into a person array. The number of threads and which threads will change each time I run it. I'll run it a couple of times, and each time you might see just a couple of threads, or you might see as many as there are in the fork join pool's connection pool. In my own case, that's 15, but yours may be different, plus the main thread is also processing data. Since this video is getting a bit long now, I'll bring it to a close. In the next video, I'll pick up at this same point in the code and continue to talk about additional concurrent classes as well as atomic variables. I'll see you in that next video.